The next phase of the machine learning pipeline after training and optimization is performance measurement. So under performance measurement, we devise methods which we'll be able to use to know whether our model is best adapted for our data set and can be used to do predictions. Several performance measurement criteria exist. We have accuracy, precision, recall, F1 score, specificity, and the confusion metrics. They can be summarized in a receiver operating characteristic curve and an area under the curve comparison. Let's get started with the data. Suppose we have this data set. That's start first with this one, where we could predict whether a person is going to have the coronavirus at the end of the month from counting the number of outings that person did in that month. So this person had 12 outings out of 30 days. We have here status 0, 5, 0, 15, 1, 12, 0, 14, 1, 20, 0, 21, 10, 0, 14, 1, 8, 0, 14, 1. It should be noted that this is not a real data set, as it's very possible that just one outing could lead you to get infected with the coronavirus, whereas you could go out, say 30 days on 30 and you never get infected. But we're just like trying to say that the more outings, yeah, or this data set that we've created, which is not a real data set, it's trying to say that the number of outings affects whether you are going to have coronavirus or not. Now, after plotting these values, that is this for this first data set, this is exactly what we have. And using a logistic regression algorithm or using a logistic regression model, we're having a case where for all values greater than 0.5, our model actually predicts correctly all the values. That is, we have all these different values which are predicted as status 1. That is, we suppose that after this number of monthly outings that at this point, if we come down here, after this number of outings going to the right, all the values for status is 1, and from this point going to the left, all the values for status is 0. We then come up with the confusion matrix. Basically, a confusion matrix is made of 4 different parts. That is a 2x2 matrix like this. So here we have actual and then predicted. So actual is what we get from the data set, and predicted is what our model tells us. And that's actually the essence of this part on performance measurement, where we want to compare what the data set gave us and what we actually predicted. So this TP stands for true positive, this FP false positive, FN false negative, and TN true negative. Now let's let the true statement to be for 1 and the false statement to be for 0. So true positive here signifies all points which actually should normally fall under 1. So we repeat, the true statement is for all points which normally fall under 1 and which our model predicts as 1. So it's a true positive. So true, it's actually a 1 and our model predicts it as 1. So we can say this point, for example, is a positive and it is true by our model. So our model tells us that this point is actually positive. So that's why we call it a true positive. Now, counting all the true positive points, we have 5 of them. And how do we get that? Using our model, we have 1, 2, 3, 4, and 5 for the repeated points. The repeated point actually is gotten at the level of 14. So if we look at this, you should have one of these points repeated. So that's why you have the 5 points, or they haven't 3 repeated points. So normally this plot shouldn't have one of these points. So that said, we have 5 true positive data points. Now let's move on to the next. Let's look at the true negatives. For true negatives, they are actually negative points. That is, according to the data sets, they are actually zeros. And true, that is to say, our model predicts that they are negative. So they are actually negative points. So another way you could look at this is to say actual negatives. and here actual positive. So these are actual negative points, so we call them true negative points, points which are actually zeros, and our model predicts them as zeros. And if we count these points here, we also have 5 points. So this our model is kind of like a perfect model for this data set. Now for the false positives, let's understand this notion of false positive. Now for a false positive, basically here we start with a positive, so we are having a data point which is actually negative, but our model predicts it as positive, so that's why we call it a false positive. Now for false negatives, we have a model which is actually positive, but our model predicts it as negative, so we call it a false negative. And in this data set, we have no false negative and no false positive. For our first performance measurement criteria, we have accuracy. Now, accuracy is given by the true negative plus true positive divided by true negative plus true positive plus false negative plus false positive. So we're adding this with this and dividing by the sum of all these elements. In that case, we have 5 plus 5 divided by 5 plus 5 plus 0 plus 0, which is 1. So we have 100% accuracy. That is, if we multiply this by 100%, knowing that the accuracy ranges from 0 to 1. Now let's look at this other data set where we only have 3 elements which have the status to be 1. And if we consider this model, we see clearly here that our model tells us that for all values below this point, because we are supposing this, we are taking the 0.5 mark, this is the 1 mark, this is the 0 mark, and this is the 0.5 mark. So for all values less than this, so we having this number of monthly outings, if we extrapolate to this point, all values below this, our model considers them to actually be 0 values. So we're supposing that all values less than this number of outings, we could take this value to be 15, for example, because in this case, these 2 14s lie here, and then this 16 is the only value which lies here. So say for all values less than the number of outings, which in this case is 15. So if you go out 15 times and below, our model sees it to actually have a status of 0. So our model tells you that you are not going to have the coronavirus. But then this is very bad because we have 2 of these values which actually are left out. So normally our model should have done something like this. So we should have come instead like this and up this way, such that these 2 values would have been up. But we are going to work with this model as it is, and that's the aim of this section, as we want to look at how well or how poorly this model performs. And then again, we have the confusion metrics, we have the true positives, the false negatives, which I'll go a little bit behind. So as a little in-class exercise, you could simply pause at this level and calculate the true positive, false negatives, and true negatives. And then when you're done, you could compare with the values we're gonna have. So you could pause and then start when you are ready. So let's continue. We have the true positives to be only 1. So why true positives only 1? That's because we have only 1 value which is actually positive, that is actually having a status of 1. So it's only one of these data points we have which is actually having a status of 1 and which our model predicts to be 1. So that's why we call it a true positive. It is actually a positive according to our model, and there are only one of these data points, or there is only one of this data point. And the next we have the false negative. So for the false negatives, we're trying to find all those values which are actually positive, but our model sees them as negatives. So they are false negatives. They are, you could say, bad negatives. So instead of them being positive for our model sees it as being negative. In this case, we have these 2 points. So if our model had a number of monthly outings threshold to be say 13, we would have had a better result, as these 2 values would have gone up. But now this doesn't seem to be the case, as our model says these two values to be negatives, and they are actually false negatives. And then the next we have false positives. So false positives depicts the number of values which are not positives, but our model sees them as positives. In this case, we have none of such values, as most of our values are considered to be negatives by our model. And then finally, we have the true negatives, values which are actually negatives, and the model predicts that they are negatives. So in this case, we have the 7 remaining values. Now let's go ahead to calculate the accuracy. True negative plus true positive divided by true negative plus true positive plus false negative plus false positive, which is 1 plus 7 divided by this, or divided by 10, which gives us 0.8, that is 80% accuracy. We see clearly how the accuracy has dropped from 100% to 80%. Next, we move to precision. Precision can be described as the way in which our model is able to minimize the false positives. So for our model to have a precision of 100%, as in the case of this model and this other model, all data points flagged as positive have actually to be positive. So in this case, we have all these data points which are positive according to the data set and also according to the model. With this point is positive according to the data set and also according to the model. So in this case, we have no false positive. That is, we have no data point which is flagged positive, which isn't supposed to be positive. So in this case, we see that our model is 100% precise. The next performance measurement criteria is the recall or sensitivity. For this first model, we have a recall of 100% still. With a recall, we are measuring the model's ability to classify negative samples from the data points as actually negative. So in this case, since our false negatives are actually 0, we have a recall of 1, or a sensitivity of 1. In this other example, we have a recall of 0.33. Now, notice that the false negatives, that the number of false negatives are actually 2, whereas the number of true positives 1. So we have this value. We've just seen how using one performance metric, that is the accuracy, gave us 80%, meaning maybe our model is doing good, whereas another metric gives us 33%. And for the same model, we'll see that it's actually doing very poorly, whereas the precision is at 100%. This simply tells us that depending on the problem we're trying to solve, our model can be seen as one that is very good, as in this case, or one that is very bad. Supposing this model was taken into production, it means many patients will be classified as not having the virus, of which they actually have the virus, which is very dangerous. Meaning we'll have so many more patients who are going to stay without maybe taking treatment or some other care, and who later on may lose their lives. Whereas initially, if we're using only accuracy, we may feel like, okay, at 80% accuracy, our model is good enough for production. But looking at the recall, we see that this model is gonna cause much disaster in production because its recall is very low. Hence, many people will be classified as not going to have the disease when they actually would have it. Nonetheless, there are some problems where having a recall of, say, 33% isn't or may not be much of a problem. So depending on your task, you may want to make sure that your precision is as high as possible or your recall is as high as possible. And even in some tasks, you want that the precision and recall are both as high as possible. Hence, the accuracy should be tending towards 1. Our next performance measurement criteria is the F1 score. Now, the F1 score is kind of like the average between the precision and the recall. In this case, we have an F1 score of 1, and in this case we have an F1 score of 0.5. Now notice that that is taking only the average, that is we have 1 plus 0.33 divided by 2, we're going to have something like 66.6%, whereas the F1 score tends to penalize extremes. So what the F1 score gives us here is 0.5, which is less than 66.6%. And this has to do with the fact that one of the values that's between the recall and the precision, one of them is very low. So whenever you have such values, your F1 score is going to be penalized, or your F1 score is going to penalize the fact that you have this recall which is kind of very low. So that's why we have 0.5 instead of 60, or instead of 0.666, that is 66.6%. Now we have 50%. For the next, we have specificity. Specificity is defined as the number of true negatives divided by true negatives plus false positives, which gives us 1. And here we have true negatives over true negatives plus false positives, which gives us 1. Then we move on to the confusion matrix, which basically is a matrix made of these 4 elements, that is TP, FP, FN, TN, and this other TP, FP, FN, TN. So this is basically our confusion matrix. Let's modify the threshold which our model uses to differentiate whether based on the number of monthly outings we have a status of 1 or a status of 0. So suppose this threshold is moved from 0.5 to 0.01. In that case, we're going to be having 2 of these values, that is these 2 points, which are going to be considered as status 1. That is, we're going to consider these 2 data points as having the virus. So in this case, we have the number of true positives, which is still 5, because we have 5. The number of false positive, which is 2, because these 2 values are going to be up this time around. So we're going to have these 2 which are considered to be up, while this line comes just almost at 0. It moved from 0.5 to 0.01. So these 2 actually are going to move up, and we have the false positives to be true. So we have these 2 which are actually false positives. The false negatives to be 0. That's because we have actually no positive value which is below. So we have no false negative. Then the true negative, or the number of true negatives, is 3. That's because here we are going to be left with 1, 2, 3 negatives, which actually are true negatives. Then from this, we could recalculate the recall. The recall value in this case is still 1. That's because the number of false negatives are actually 0. Then we have the specificity. This S stands for the specificity, which is TN, in this case 3 divided by 3 plus FP. FP is 2, so 3 divided by 5 is 0.6. So our specificity moves from 1 to 0.6. And also, if we move this threshold from 0.5 to 0.99, we're going to be having the number of true positives to be 4. Now the reason we have this is actually because we're supposing that this point is just below the 0.99 mark, so it's going to be considered as a negative. So the number of true positives move from 5, which was initially 1, 2, 3, 4, 5, to just 1, 2, 3, 4. So now we have 4. Then the number of false positives is 0. So all data points marked as positives are actually positive, so we have no false positive. The number of false negatives is 1, because this point becomes a negative, which is not true, so we have this point to be 1. The number of true negatives, 5, so all these other points are true negatives. We have now a recall of 0.8 and a specificity of 1. We shall see now with this next example why it's important to have these different values, or why we are even doing these calculations with different thresholds. So we move to this other example. When we have the threshold to be at 0.1, which is this, the number of true positives equals 3. Now, the reason why we have 3 instead of 1 as previously is because when you have at this point, let's say we have this threshold which leads from 0.5 to 0.1, it means that we take from this point, that is where this threshold meets our model. Taking from this point right down to this axis, we have all these values are considered to be of status 0. So from this to this, 0. Now from this point coming down, all this to the right are considered of status 1. So it means these 2 points automatically become of status 1. So normally these 2 points step up and get to this level. So we have now these 2 points to this level, telling us that the number of true positives are 3, since these 2 were initially positives. And now with this threshold, our model correctly classifies these 2 values. The number of false positives 0, the number of false negatives 0, and the number of true negatives 7. So we have the 7 values still. So this gives us a recall of 1, accuracy 1, specificity 1. Now let's consider that our threshold goes to 0.95 instead of 0.5. So we move to 0.95, and what's interesting to note here is our model, that is all values from this point where this line meets our model, suppose it meets at this point, all values from here to the left are considered to be of status 0. So once the number of monthly outings are below this threshold, we consider that you are going to have the virus. So in this case, the number of true positives is 0 because there is actually no true positive. This value will come down. The number of false positives 0. The number of false negatives 3. These 3 values. So we have this, and this is going to come down. The number of true negatives 7. R is equals 0 and specificity equals 1. After understanding these concepts, we can look at the ROC and the AUC. ROC signifies receiver operating characteristic, and AUC area under the curve. We shall start with the ROC. Now, suppose we have this, we are plotting the true positives, the true positive rate against the false positive rate. The true positive rate is the sensitivity, and as we saw previously, sensitivity equals recall, so we're plotting the recall against 1 minus the specificity. Now, putting these values, we start with this 0, that we have the origin, up to 1, and then up to 1, so it's always like this. Then we take values, that is the idea or the main idea we are using this ROC is to actually test all these values. Now let's come back to this example. You notice that when we selected this 0.1, we had a different confusion matrix. When we selected this, we had a different confusion matrix with different values for TP, FP, FN, and TN. So this means for many other values, because there's an infinite number of values, we could select between 0 and 1, since our threshold can only go between 0 and 1. So for all those different values, we would have an infinite number of confusion matrices. Now, a way in which we could summarize all this confusion or all these possible confusion matrices is by working with the ROC. So that is exactly what we are going to do here. Now, for this data set and this model, if we consider points, say 0.1, 0.2, 0.3, 0.4, 0.5, up to 0.9, our recall will always be at 1. So no matter what we do, so far as we're in the range 0.1 to 0.9, our recall always be at 1. Reason being that in this range, nothing changes in our model. So all these values always remain intact. So if we're at the point here, for example, and reaching down, all these values to the left, and then even if we go up to this point and cutting this way, all these values are still considered to be to the left, and all these values are still considered to be to the right. So our model doesn't have any change, or there is no point that leaves from status 0 to status 1 or status 1 to status 0 when we are in this range 0.1 to 0.9. And our recall, as we had calculated, is 1. As the recall is equals 1, our specificity 1, so we have 1 minus specificity, which is 0. So we already have this first plot. Now we could move to the next. Suppose we are working with 0.99, so our threshold now is 0.99. At 0.99, as we had seen, our recall was 0.8, so that's why we have here 0.8, and our specificity 1, so we are 0, so that's why we are at this point. Then when we have our threshold at 0.01, as we had seen, the recall is equals 1, the specificity equals 0.6, hence 1 minus specificity equals 0.4. So that's where we are at this point. And then we could link all these different points to form what we call the receiver operating characteristic curve, or the ROC. So this linkage, or this linking of all these points, gives our ROC. Now, this is not the only possibility. It was possible that maybe for a different model and different data set, we will have an ROC like this. So for a different case, we'll have a situation where our recall will never be up to 1, no matter how we play around with the values of the threshold. So as you can see, this curve kind of summarizes the infinite number of possibilities we could have. Although generally, to plot this curve, we kind of choose, say, 10 or 20 values between 0 and 1 at regular intervals, and then link all this to form a curve like this one or this other one. So as we were saying earlier, depending on whether you want a high recall or a high precision, you will just come and choose a particular point. So suppose we want a high recall, we may want to come and choose a point which is around, say, for this second curve, we want to choose a point which is around this. For the first curve, which is what we calculated using this data set and this model, we have this curve. So basically, if we want a very high recall, we just come and get to this point. And a high recall, or a recall of 1 and specificity, or 1 minus specificity of 0, at this point tells us that any threshold we choose between 0.1 and 0.9 will give us that recall. So this curve kind of like helps us in finding the best threshold for our problem. And as we saw previously, not all problems may need a very high recall, and not all problems may need a very high precision. So depending on our problem, we may want to maybe prioritize a high recall or prioritize a high precision. And in some cases, we may even want to prioritize both. And that's actually most of the cases where we want to have our accuracy as high as possible. And then it should be noted that these two curves actually represent two different models. So the different points represents the possible thresholds and their varying recalls and specificities. And then these two different curves represent two different models. So when dealing or working with machine learning problems, we may want to play around with the thresholds, or even play around with different models. So you can have 2, 3, 4, 5 different models, and then plot these ROC curves, and then from there you could do some comparison. It's seen clearly that if we have a model here, this model 1, and then this as model 2, or say model A, model B, this model A is going to be preferred compared to model B, simply because the area under this curve is greater than the area under the curve of this. So the area under this curve is this, whereas the area under this curve is all this plus this extra portion. So this is going to be our best model. For this other data set, we have, as we had seen, we have 1, we have the origin, we have 1, we have the sensitivity plotted with 1 minus specificity. Now at 0.1, as we have seen here with this threshold of 0.1, our recall was 1, s equals 1, hence 1 minus s equals 0. So we are at this point. At 0.95, we have r equals 0 and 1 minus s equals 0. That's why we are at this point. And then for this, for all other values, say between 0.3 and 0.9, that is from around this point to a certain point here, we're going to have no change, since our model will end up having the same prediction. So for all these values, we still have what we had in this coefficient matrix. Not forgetting that this is one coefficient matrix, this is another, and this is another. So for this coefficient matrix, which represents a threshold between 0.3 and 0.9, we have this point, that is the recall 0.333, which was this, and then the specificity 1, which gave us 1 minus 1 is 0, so we are at this point. And with this, we could put our ROC curve. We can draw another possible ROC curve, and if we have these two models and we have to compare, we're going to pick this other model compared to this other one. So we've seen clearly in this section that it's important to know exactly what you want as results. So if the team had published results for this data set and this model, saying that this model does well with an accuracy of 80%, people may tend to use this model in doing these predictions, whereas this model is kind of having a very poor recall, which is very bad, because this model will tell people that they don't have the virus, whereas they actually have the virus. So it's important to know what metric is very important to you. As in this case, our recall is a very important metric, because it tells us that, or tells us how our model behaves when it comes to false negatives. We could take another simple example. Now, suppose we have, or suppose these inputs are changed to, say, an image on Twitter, and then the Twitter model or algorithm has to say whether that input or that image has to be viewed by everyone or be viewed only if that person decides to. So we're supposing that being able to view by everyone, you have a status of 1, and not being able to be viewed directly is a status of 0. I guess you may have used Twitter and had a situation where you have an image which you must decide to view before actually viewing it directly, whereas most other images and videos and multimedia are just seen on your timeline automatically. So we have those two possibilities: status 1 if you could just view it easily, and status 0 if not. Now in this kind of situation, you can afford to have many false negatives, that is, many images which are going to be flagged as not to be viewed directly, because that will cause less harm as compared to having many false positives. As if we have many false positives, we have so many images on people's timelines when they do not actually want to view those images directly. So that may cause some trouble. So in this kind of situation, we find that we instead want to have, or we can afford to have, many false negatives. So in that case, we can afford to have a low recall, but we make sure we have a high precision.